Now we'll get more into detail about the line of best fit. How do statisticians find the best line to summarize a linear pattern in data? The line that best fits the data is the line that makes the best predictions. The closer the line is to the data, the better the predictions from the line. Now we'll look at an example where prediction error and the line of best fit, the line of best fit creates prediction error. Let's begin with a simple data set with only 5 data points. Which line appears to be a better summary of the linear pattern of the data? So it looks like the one on the left is closer to the bottom 3 points. Those points are either on the line or very close to it, but the top 2 are not. This one, though, it looks like it's trying to take a more middle ground approach. It's try to be equidistant from all of them if it can, I think. So that's a good question. Was it better to be very close to the majority of the points and further from the minority of the points? Or is it better to be right in the middle? You're not intersecting with any of those points, but you're kind of not too far away from any of the points. Let's look down here. Here are some initial observations. Okay. The line on the left comes very close to passing through 2 of the 5 points, with the point 12,7 also very close to the line. For these points, the predicted y values from the line are very close to the observed y values, which means very small predicted error. The point 8,13 and 17,14 are relatively far from the line, which translates into larger amounts of prediction error. The line on the right does not pass through any of the points. It appears to pass through the middle of the distribution of the data. The predictions from this line will all have some error, but none of the predictions will have a large amount of error. To visually represent the prediction errors, we drew a vertical line segment from each point to the line. The length of each vertical line segment is the amount that the predicted y value deviates from the actual y value of the point data. This length is the predicted error. So just showing of all the points in the distribution, how far away are they from the actual line itself? So you notice that the distance here between those 2 points are fairly high, but there's not much of a distance between the other 3 points in the line. Here, all the distances aren't too long, but none of them are on the line or really that close to the line. So which line best fits the data? Let's scroll down a little and see. The line that best fits the data will have the smallest overall prediction error. At this point, identifying the line with the least amount of prediction error is a judgment call. We need a more precise way to measure the overall prediction error. The most common measurement of overall prediction error is the sum of the squares of the errors. So you take all those distances and square them, and then add them together. SSE, sum of squared errors. The line with the smallest SSE, or sum of squared errors, is called the least squares regression line. We call this line the line of best fit. But you can imagine this one had 5 data points. What if it had more than 5? It had 10, 20, 30, 40. Trying to take all those distances, figure out what they are, first of all, square them all, and then add them together and compare that to another line. It would be a lot of work and very difficult and easy to make a mistake if you do it by hand. So definitely technology would help on there. Now look at an example for the sum of squared errors. We want to adjust the line until the overall prediction error for all points together is as small as possible. So I think this will really answer the question, is it better to be very close to the majority of the points, like the leftmost graph was, or the line on the leftmost graph was, or kind of try to take a middle ground where you're not really super close to any points, but you're not very far away from any points as well. When we locate the line of best fit, the sum of the errors or deviations from the line will equal the sum of the errors or deviations below the line. Does that sound familiar? This is similar to what we discovered about deviations from the mean during our development of the standard deviation. The sum of the errors or deviations above the mean equal the sum of the errors or deviations below the mean. To fix this issue, statisticians squared the deviations from the mean in the calculation of the standard deviation, and they do the same thing here, square the errors. That's because a distance from the line above would be a positive distance, like this would be a positive SSE or whatever. And then if it's down here, though, the distance would be a negative number. They don't want those two to cancel each other out. You know, if I happen to have the same distance above and below for 2 different points, they'll cancel each other out. And if I were to try to calculate all the distances added together, it would be like neither of these points even had any distance because they'd add up to 0, you know, a positive and a negative. So that's why they square all the data values to make sure that they're all positive. Square just meaning multiply it by itself. So if it's a negative times a negative will be a positive. Of course, if it's a positive times a positive will be a positive. Now below are the scatter plots. As before, each vertical line represents the error in a prediction. For each data point, the squared error is equal to the area in the yellow square. The SSE, or sum of squares of the errors, is the sum of these areas. The least squares regression line is the line with the smallest SSE. Now let's scroll down and look at those. Okay. When we compare the sum of the squares of the yellow squares, the line on the left has an SSE of 57.8. Okay. The line on the right has a smaller SSE of 43.9. So therefore, that means that this is a better way to go, is where maybe your line isn't super close to any of your points. It might not intersect any of them, but it's not too far from any of the points either. Using the least squares measurement, the line on the right is a better fit. It has a smaller sum of squared errors. But is the line on the right the best fit? The answer is no. We can use StatCrunch to find a line with the smallest SSE for this data. It's actually y, they write it there, y equals 6.72x plus 0.26x. Wait, what? Oh no, sorry, there's no x on this guy. This has an x, sorry about that. The SSE is 41.79, which you can tell is smaller than either of these SSEs. The line of best fit, the main point here is the line of best fit is the line that comes as close as possible to all the data points. And by as close as possible, we mean that the sum of the squared errors is as small as possible. The line with the smallest sum of squared errors is appropriately named the least squares regression line.